exercises on the topic vector space. So these are exercises from 1 to 12. So what is the question? Determine whether the set is vector space under the given two operations. So if you observe the first, V is equal to R square, set of all order pairs with real numbers, real entries. Then x1, y1 addition is usual addition, and scalar multiplication is what? K x1, y1 is k x1, comma y1. So already we have seen the answer of this question. So we have to give the counter example. This is not vector space. Similarly, the remaining examples, here the definition of addition is not usual addition. And so it may or may not be vector space. So these are the problems for homework from 1 to 12. The operation, two operations, addition and multiplication are given. We have to determine whether the given set is vector space or not vector space under the given two operations. Obviously, the addition or scalar multiplication definition are not usual addition or usual scalar multiplication. So the answer of these problems are here. So the first, for example, the first not vector space, assume M2 is fails. So I have to give the counter example of assume M2. Not a vector space, the second answer of second problem, because A1, A3, A4, M2 fails. So I have to give any one property that fails by using counter example. So similarly, third answer of third problem, not vector space, assume M4 fails. Not vector space, number 4, not vector space, assume M4 fails. That is why to write the counter example. We have to give the counter example for, suppose M1 is not, M1 fails. We have to show M1 fails, the property M1 fails. So by using counter example. So the sixth number is S. The answer is yes, means it is a vector space. That is why to write the all 10 properties, not vector space. The seventh answer, closure assume C1 fails. So we have to write the counter example for closure assume. 8 number and 9 number are vector spaces. Similarly, 10 is not vector space, 11 is not vector space, 12 is not vector space, 13, 14, 15 are yes answer means are vector spaces. 16 is not vector space. We have to give the counter example for C2. Similarly, the example 17, 18, 19, 20, 21, 22, 23, 24, 25. So answers are given. Here is the problem. So up to 12, the problems are R square, R cube. That is the set of order pairs, set of 3 tuples. And from 13, the problems, the V is the set of functions. So as far as the exam concerned, these first 12 problems are important. So, and now if you observe from 21, the vector set, the V set is the set of 2 by 2 matrices of the different types. So where to write the answer of these problems. Most out of these problems, the important problems are the set which is not vector space. That are important problems. So we have to give the counter example, and we have to write the property which fails for the, out of the 10 property, we have to write the property which is fails for the set. So solve all these exercise problems. Okay. Answers are given. Next is theorem or properties. Some properties of vector spaces. Vector space. So V is a vector space, and U bar is a vector in V. That is the element of the vector space V. And K be any scalar. Then we have to prove 0 into U bar is 0 bar. K into U 0 bar is 0 bar. Minus 1 into U bar is minus U bar. K U bar is 0 bar if and only K is equal to 0 or U bar is equal to 0. So first proof of the first, 0 into U bar. 0 is the scalar. Here 0 is the scalar 0. This 0 bar is the vector 0. So what is the difference between scalar 0 and vector 0? So if we consider suppose the R3, the vector space R raised to 3, then what is 0 bar is the 3 tuple 0, 0, 0. Right in round bracket 0, 0, 0. And simple 0 means the real number 0. Okay. So this is reference between simple 0 and vector 0. So we have to prove the first property. So 0 plus 0 is equal to 0. Then multiply by u bar on both sides. So then we have 0 into u bar into 0 into u bar is equal to 0 into u bar. By using the property axiom number 4, that is k plus l u bar is k u bar plus l u bar, like that. So k and l are scalar, 0, 0 are scalar. So then add minus 0 into u bar on both sides. Minus 0 into u bar is what? Is negative of 0 into u bar. So add 0 into u bar minus 0 into u bar on both sides. And then by using associative property, we have shift this bracket to these two. So 0 into u bar is 0 into u bar plus minus 0 into u bar, minus 0 into u bar. Okay. And is equal to 0 into u bar, 0 right here bracket minus 0 in bracket, then complete the bracket after u bar, minus 0 u bar, like this here, 0 into u bar minus 0 into u bar, and then RHS as it is, and then 0 any vector and its negative is 0 bar. So 0 into u bar and its negative 0 into u bar, addition is 0 bar. Similarly 0 into u bar and its negative 0 into u bar is 0 bar. And if we add 0 bar in any vector, we have the same answer by using A3. So 0 into u bar plus 0 bar is 0 into u bar is equal to 0 bar. And that is why to prove 0 into u bar is 0 bar. Similar proof for this, k into u 0 bar is equal to 0 bar. K is scalar. So we have 0 bar plus 0 bar is equal to 0 bar. Multiply k bar on both sides like this. Start like this. 0 bar plus 0 bar is equal to 0 bar. Then multiply by k to both sides. K 0 bar plus 0 bar is equal to k 0 bar by number 3. 0 bar plus 0 bar is 0 bar. Then k 0 bar, apply the property M1. That is k u bar plus v bar is k u bar plus k v bar. So k 0 bar plus k 0 bar is equal to k 0 bar. Then add negative of k 0 bar on both sides. Similar to this. Similar. Add minus k into 0 bar on both sides, and then k into 0 bar minus k into 0 bar is 0 bar, like this. Shift the bracket and write the value is equal to k into 0 bar minus the k into 0 bar is 0 bar 0 bar, and then k into 0 bar is 0 bar. So write same proof like this. Add both like this. Add both side minus k into 0 bar, minus k into 0 bar on both sides after this step. So we have this k into 0 bar is 0 bar. Then third one is we have to prove minus 1 into u bar is minus u bar. Minus 1 into u bar is minus u bar. That is, what is minus u bar? Minus u bar means negative of u bar. So we have to show negative of u bar is minus 1 into u bar. What is to show minus 1 into u bar is minus u bar? That means we have to show minus 1 into u bar is negative of u bar. So when minus 1 into u bar is negative of u bar, if the addition of minus 1 u bar and u bar is 0 bar. So consider u bar plus minus 1 into u bar, and we have to show it is equal to 0 bar. So we write u bar as 1 into u bar by axiom number 4, M4. What is 1 u bar is u bar. So, and then take u bar as common by using axiom number M2 by reverse use of axiom number M2. What is M2 axiom? K plus L u bar is k u bar plus L u bar. So k u bar plus L u bar is k plus L u bar. By reverse way, we have to write, we have to use this axiom number M2. So we have this minus 1 plus minus 1 into u bar. And minus 1 plus 1 is 0. Simple 0. Usual 0 into u bar. And 0 into u bar is 0 bar by using the property number first. So 0 into u bar is 0 bar. And therefore we have u bar plus minus 1 into u bar is 0 bar, means minus 1 into u bar is negative of u bar. Minus 1 into u bar is negative of u bar. That is minus 1 into u bar is equal to minus u bar. Okay. Then we have to show, prove the fourth number, k u bar is 0 bar if and only if either k is 0 or u bar is 0. So if k is 0, then what do we have? The 0 into u bar is 0. Not if k is 0, then what do we have to show? 0 into u bar is 0 bar, and we have the this 0 into u bar is 0 bar. And if u bar is 0, then we have to show k into 0 bar is 0 bar, and that is the proof number 1 and 2. So if k is 0 or u is 0, so suppose ku bar is 0. If k is 0, then nothing, there is nothing to prove. So if k is 0, either k is 0 or u is 0, then the case turns out to 1 or 2. That is, and then we have ku bar is 0 bar. So if k is 0, then what is k 0 bar? So if k is 0, then we have to show k into u bar is 0 bar. And if k is 0, then 0 into u bar is 0 bar by using 1. And if u bar is 0, then k into 0 bar is 0 bar by using case number 2. Okay. So if k is 0 or u bar is 0, then ku bar is 0. This is the one way proof. Then conversely, assume k. This is the Epan-Onlip type theorem. This is the Epan-Onlip type theorem. Epan-Onlip. So we have to assume this, either k is 0 or u bar is 0. Then we have to show this. So this is very obvious. If k is 0 or u bar is 0, then ku bar is 0 by using 1 and 2. Now the converse part is assume that ku bar is 0 bar, and we have to show either k is 0 or u is 0. So conversely assume that suppose ku bar is 0 bar, and what we have to show, either k is 0 or u is 0. But if k is 0, then there is nothing to prove. Okay, if k is 0, because we have to show either k is 0 or u is 0. Suppose k is 0, then there is nothing to prove. So we assume that k is not equal to 0. Then k being a scalar and 1 by, and there is a 1 by k, that is k exists. K into 1 by k is 1. So k is not equal to 0, then 1 by k exists. Its inverse exists. So multiplying both sides by 1 by k to this k u bar is equal to 0 bar, multiplying 1 by k, we have this. And then 1 by k into k u bar, 1 by k, any scalar into 0 bar is 0 bar by using 2, by using proof number 2. And 1 by k into k u bar by using axiom number m3, k l u bar is k into l u bar. Okay, so by axiom number 3, m3. And then 1 by k into k is 1, because 1 by k is the inverse of k, and 1 into u bar is u bar, and so we have u bar is 0. That is, if k is not equal to 0, then u bar is 0, and therefore this is proof that this ku bar is 0 bar if and only if either k is 0 or u bar is 0 bar. Okay, so the proof is not in the two part. Assume this and prove this. This is first part, and then assume this, and we have to prove this. So if ku bar is 0 bar, then either we have to show k is 0 or u is 0. If k is 0, then there is nothing to prove. So assume k is not equal to 0, then multiplying 1 by k on both sides, we have u bar is 0. So if k is not equal to 0, then u is equal to 0. So these are some properties on the vector space. 0 into u bar is 0 bar, k into 0 bar is 0 bar, minus 1 into u bar is minus u bar, and similarly the fourth one. So these are the properties of the vector spaces, and these are the examples for exercise. For example, if you take M2, this is A00V. So in this example, this is the set of matrices 21. So if you observe the answer, the yes, it is a vector space. So we have to show the 10 properties. If the set is vector space, then we have to write the 10 properties. So solve all these examples. These are also examples from vector space chapter. Depends on vector space. So we have to write the answer of all these exercise problems. So this is about the vector space. That is the set, when the set is vector space and when the set is not vector space. So now in the next lecture, we have to see the subspace, the topic subspace. So we'll discuss the topic subspace in the next lecture.